Okay, so we've been talking about the dissociation of acids and bases in solution. And we're going to talk about the dissociation of ionic compounds as well. And so I just want to take a moment to review what we mean when we say something dissociates in solution. So the name for any kind of compound that breaks apart in water is an electrolyte. So an electrolyte is something that dissolves in water to make a conducting solution of ions. So for example, if we have salt, NaCl or any kind of other salt that we've looked at, and we put it into water, it breaks apart to make the negatively charged ions and the positively charged ions, and that's because the water molecules can surround those, make this solvation shell, where the negatively charged end of the water attracts the positively charged ions. The positively charged end of water attracts the negatively charged ions. Coulombic attraction, it pulls the ions apart in solution. So let's make a little table of things that are strong electrolytes. Things that are strong electrolytes, things that are weak electrolytes, and things that are non-electrolytes. Okay? So first of all, if we say something's a strong electrolyte, so strong acid, strong base, for example, that means it's 70 to 100% dissociated into ions when it's in water. On the other hand, something that's a weak electrolyte is going to be less than 70% dissociated in water. So as far as the things that we've seen that are strong electrolytes are strong acids, again, those are all listed on the equation sheet. So those are molecules that lose a hydrogen to make an anion and a proton in water. And all soluble ionic compounds are going to be electrolytes. For example, we've seen that sodium chloride dissolves in water and sodium hydroxide dissolves in water. And in just a moment, we'll look at the details of what exactly are the properties of ionic compounds that dissolve in water. And in fact, we'll just have a table that tells us which ones dissolve in water and which ones don't, and for the ionic compounds. So for weak electrolytes, the things that dissociate less in solution, really the only examples we have of these are weak acids and bases, things like hydrofluoric acid, also acetic acid, CH3CO2H, and weak bases like NH3. Those are the things that are weak electrolytes. They don't dissociate very much in solution. They stay pretty much intact the way that they came in. Okay, and then that leaves us this category of non-electrolytes, things that really don't dissociate in solution at all. And that's going to include, of course, water, H2O, but also most carbon-containing molecules. Okay, so that means, octane, C8H18. That includes alcohols like ethanol or methanol. Methanol is CH3OH. That's not going to dissociate into ions in solution. And also sugars, so C6H12O6 is fructose, or the same formula works for glucose. Those are all carbon-containing molecules. They're not going to dissociate into ions in solution. So again, remember, anything that contains carbon, if it's not acetic acid, CH3CO2H, if it's not that, it is a non-electrolyte. Acetic acid is a weak electrolyte. All other carbon-containing molecules are non-electrolytes. And I'm going to let you know if something is a molecule that's an acid if it's not on that strong acid list. Okay? Acetic acid has it right in its name. Hydrochloric acid, of course, has it right in its name. Those are molecules, but they have acid in their name, and so we know that they're either weak or strong electrolytes. And so just to review what this means in terms of what we've looked at on the last video, if you have things that are strong electrolytes, when you write that complete ionic equation, those are going to be dissociated in the equation. If it's a weak electrolyte, it's going to start out in its basic form. If it's a weak electrolyte or a non-electrolyte, it's going to stay out in its I shouldn't say basic form, but it's going to stay out as a full formula even in the complete ionic equation. So acetic acid in the complete ionic equation is always going to look like this until it reacts and loses that hydrogen to a base, right? And ethanol would always stay in this form even in a complete ionic equation. It would never break apart into ions, so we wouldn't show it as ions. And so those structures could never get canceled out in the net ionic equation because they don't start out as ions. They have to undergo some change in the reaction. So let's look at what this means in terms of real compounds. And so first of all, let's look at some sort of made-up compounds where we don't really know what the compound is. And let's say we just have compounds A, B, and C, A2X, A2Y, A2Z. So here's our sort of starting out compound. Looks like that. And if we look at what their molecules do in solution, if we don't look at what the waters are doing, so the waters aren't shown here, which of these is the weakest electrolyte based on how it breaks apart in solution? So pause this, take a moment, and try to answer that question. So if we're looking for the weakest electrolyte, we're looking for the one that breaks apart the least. So A is the one that really doesn't break apart at all. We only get, you know, essentially one molecule that broke apart to give this. Here, everything is broken apart. Here we've got a couple of different molecules that broke apart in solution. But here only one did. So this has to be the weakest electrolyte. Okay, so A is the answer to that question. So again, if we were to think of things that act this way, the things that break apart a lot, like compound B did in the previous question, that would be something like CaCl2 or H2SO4. Things that acted like weak electrolytes, like maybe A or C from the previous question, would be something like lead chloride, PbCl2, doesn't really break apart very much at all. We'd say it's not very soluble in water. And things that are non-electrolytes that are never going to break apart in water are things like methane. So if we know a little bit about how different compounds are going to act in solution, we can use that information to predict the outcomes of what we call precipitation reactions. So we've seen how to predict acid-base reactions. Let's look how to predict precipitation reactions. So just as an example of what we mean when we talk about precipitation reactions, let's look at the reaction of potassium chromate with barium nitrate. So here we've got soluble ionic reactants that yield some insoluble product. If we had two insoluble products, it would be really hard to get either of them back in a pure form. So we really, in a precipitation reaction, want just one type of product. There could be one type of solid product. There could be two. That would still be a precipitation reaction, but it would be not a very useful precipitation reaction in terms of the chemistry. So what's happening here is we have ionic compounds that we start with, and they're going to change partners. So we call this a double displacement reaction. So we've got the potassium with the chromate over here, and now the potassium bonds with the nitrate, and the barium bonds with the chromate. And the reason that happens is because every time a barium meets a chromate, it's going to leave the solution. It's going to become a solid and fall to the bottom. And so we get a net reaction of barium taking out the chromate, and what's going to be left in solution is the potassium with the nitrate. So here's what this reaction actually looks like in the lab. The potassium chromate is this yellow liquid, okay, in the graduated cylinder. The barium nitrate is in the water here, and it's clear when it's in solution. So both of those are dissolved. We pour the potassium chromate into the barium nitrate, and what we get out is this yellow solid barium chromate. And in solution, we're left with some potassium nitrate, and that's actually a clear solution. So we've got a clear solution here with a bunch of yellow barium chromate solid dissolved in it. And this is a useful precipitation reaction because then if we just get the aqueous liquid out of there, we're left with our solid barium chromate. This is similar to what you guys saw in the reaction in your lab during experiment 7. Okay, so how do we know what's going to dissolve in solution and what is not going to be dissolved? We need to look at something called the aqueous solubility. So in a more technical sense, solubility is the concentration of something that can dissolve completely in water at a given temperature. But for now, we're going to look at this as a purely black and white issue, that either it's going to dissolve or it's not going to dissolve. And we're going to look at something that we call the solubility guidelines. And these are actually given on your equation sheet. So let's just look briefly at how to use these and what they say. The way I have these set up on your equation sheet, and I think the book does something similar, is they tell you what is soluble. An ionic compound is soluble if it has any of the things on this list, okay? and there are a few exceptions on here. So it's going to be anything on this list except if they're bonded to something that's listed as an exception. So let's just talk about this really quickly. Group 1A cations, so something that has lithium or potassium or sodium in it. So regardless of what it's bonded to, so lithium phosphate Li3PO4 or potassium nitrate NO3, those are all going to be soluble. Okay, so they're going to be aqueous if they're in water. Oops, that's not even a compound there at the bottom, but NaCl, aqueous. Okay, so if it contains any of those, it's soluble. Likewise, anything that contains the ammonium cation, so ammonium phosphate, for example, would be a soluble compound. Okay, anything that contains Cl minus, Br minus, or I minus. Okay, we don't have F on there. Notice it's just the halogens except for fluorine. So Cl minus, Br minus, I minus, and that's going to be only if they're not bonded to Ag plus, Hg or mercury 2 plus, or lead 2 plus. So for example, if we had silver chloride, that would not be soluble. That would be a solid if you put it in water. But if we had potassium chloride, or if we had, let's see if I can come up with other examples, zinc chloride, zinc 2 chloride, that would be, those would both be soluble in water. Okay, so that's how we use the solubility chart. And we see that the nitrate, acetate, and perchlorate anions all make soluble compounds. So if we had, for example, silver nitrate, silver 1 nitrate, that would be soluble, okay? Or if we had, you know, zinc 1 nitrate, that would be soluble. It would be aqueous. Again, my handwriting really sucks on here today, but that's supposed to say aqueous. Okay, so that would be soluble in water. The sulfate ion is usually a part of a soluble compound, except if it's with barium, mercury 2 plus, or lead 2 plus. So, for example, if we had, let's just stick with zinc. If we had zinc 2 sulfate, that'd be ZnSO4. That would be soluble. Copper 2 sulfate would be soluble, CuSO4 aqueous. But if we had lead 2 sulfate, PbSO4, that's going to be insoluble. That's going to be a solid. In fact, that's something that shows up in car batteries. So it's something that forms in car batteries, and it's one of the compounds that can kind of flake off and can cause your car battery to be less rechargeable over time. There's a few compounds that are not mentioned on here. Generally, hydroxides will form either soluble or insoluble compounds. So as some examples of ones we might see, barium hydroxide, calcium hydroxide, and strontium hydroxide, those are all going to be soluble. Anything that's not on this table then, of course, is insoluble. So the table doesn't mention anything about lead hydroxide. So lead 2 hydroxide, PbOH2, that would not be soluble because it's not listed on this table. Let's do some more examples. I might have touched on a couple of these already, but let me pull up a slide with some compounds and let's figure out if they're going to be solids or if they're going in water or if they're going to dissolve in water. Okay, so let's go through these examples, and just to make this a little easier, I went ahead and put our solubility guidelines, a summary of that, up at the top of the slide for your reference while you work. So I think what the best thing to do is here is for you guys to actually sit down and tell me, are these going to be soluble or are they going to form a precipitate in solution? So this is really just asking the same question in two different ways. If they're going to form a precipitate, that means they're not soluble. The question here says, are they soluble? Okay, so go ahead and figure out what the state symbol would be behind each of these if I put them in water. Is it solid? Is it aqueous? Pause the video, try to do that. And I'm seeing on here, I already mentioned a couple of these, but hopefully there's enough new ones on here for you to get practice with. So if you've had a chance to do this yourself, which I hope you did before I go through the answers because you want to really practice with this, let's go ahead and see what the answers are. So barium chloride. Barium is not mentioned anywhere, but chloride is. It says anything with Cl- is going to be soluble except silver, lead, 2 plus, and mercury 2 plus. Oh, I said that completely wrong. Except lead, mercury 2 plus, dimercury 2 plus, or lead 2 plus. So barium chloride is going to be soluble. So yes, soluble. Barium nitrate, anything with nitrate is going to be soluble. So aqueous. So yes, that's soluble. Which of them is going to form a precipitate? Calcium carbonate. So calcium and carbonate don't show up anywhere on this table. So that's going to be a solid. That's chalk. So we could write PPT as an abbreviation for precipitate. So that's going to precipitate out of a solution. Cadmium carbonate, also not mentioned anywhere on the table, so that would be a precipitate. Magnesium oxide, again, doesn't show up anywhere on the table, so that's going to form a precipitate. Sodium sulfide. Sodium shows up on the table, and so that's going to be aqueous. It's going to stay in solution. Lead sulfate, we just talked about that. Sulfate is not soluble with lead, so that forms a solid precipitate. Ammonium phosphate, ammonium shows up on the table, so that's going to be aqueous. It's not going to form a precipitate. And this is a tough one. This is mercury 2 chloride. It's not dimercury 2 plus chloride, so this is actually soluble. I'm not going to ask you about the mercury compounds. They're pretty complicated in terms of their solubility. So let's look at what these things have in common. We can actually kind of start to learn a little bit about why some things are soluble and some aren't. And we won't go into this in detail till Chem 2, but if we look at, say, magnesium oxide, for example, we've got a 2 plus and a 2 minus ion. This has a really strong ionic bond, right? And so it's very hard to break apart, so it becomes a solid. It stays as a solid if you try and put it in solution. If you look at anything that has one of these group 1A cations, it's all going to have a 1 plus with something else. That's a 1 plus with a 2 minus. So the bond is not as strong, right? We looked at the Coulombic potential between two ions. We saw that if they had smaller charge product, they had a weaker bond, and that weaker bond then is easier to break apart when it goes into water. On the other hand, we saw if things are really, really big, they also have a very weak bond. So ammonium phosphate has a +1 and a 3 minus, so it's a fairly big charge product, but the ammonium and the phosphate ions are just huge compared to, say, the magnesium and the oxide ion. And so this is going to be a much weaker bond between the ammonium and phosphate than it is between the magnesium and the oxygen. And so that makes this thing break apart more easily in solution, and so it's more soluble. It dissolves easier. I wanted to mention this kind of cool little application of precipitation that nature uses. So since calcium carbonate is not really soluble in water, if any of it gets into water, there's all kinds of organisms that are going to gobble it up. And if you get it, so if you have a little bit in water, you might get teeny bits of it to dissolve, but if you put much more, it's not going to dissolve, so the organisms gobble it up and they raise the local concentration of calcium carbonate, so it starts precipitating out of solution, or they do chemical reactions that make calcium carbonate. And this is a little organism called a diatom. They're just little multicellular organisms on the seafloor, and it's taken calcium carbonate, essentially chalk, and made all kinds of cool little structures out of it to make its exoskeleton out of. And since calcium carbonate doesn't dissolve very well in water, then this guy can float around in water with his little calcium carbonate skeleton. This is actually one reason that acidification of the oceans is so dangerous to life as we know it on this planet, is we have a lot of organisms that have these compounds that don't dissolve in water, but if you make that water a little bit acidic, we saw earlier in an example on Monday that calcium carbonate does react with acids. And so, so this was the example we did on Monday. So if you have a little bit of acid in your water, it's going to start dissolving the exoskeletons of some of these organisms that use these compounds that are not soluble in water but do react with acids. And the more CO2 we have in our atmosphere, the more acidic the oceans become. So here we go. Now we're ready to make some predictions. Okay, so the reasons that we care which compounds are soluble and not, of course, is that we want to be able to predict the outcomes of precipitation reactions. So here's a reaction of silver nitrate with potassium chloride. We get a white solid out of this. And I want you to tell me, what is the precipitate? You guys got a little bit of practice on this when you did a worksheet for your experiment 7. But let's just take a moment and talk about it again. So you want to think about, what's the complete ionic equation? So what are the ions that I have in solution? What are the possible combinations of those ions in my products? And then I want to figure out which of those ones are soluble and which ones are likely to form solids, to precipitate out of solution. Okay, so let's do this. So we've got silver nitrate. So we've got Ag plus, which is in solution. Nitrate, NO3 minus, in solution. We've got potassium plus in solution. And we've got chlorine minus, so chloride ions in solution. So what can I possibly make from this? Well, I could make silver nitrate and potassium chloride, but I know that those two are soluble. So now I've got something that's insoluble. I must have made something else. So if I combine the ions in just a slightly different way, the silver, instead of being with the nitrate, if I put it with the chloride, I get AgCl. And if I take the nitrate that's left and I put it with the potassium, I get KNO3. And then I look at my solubility chart and I say, okay, Cl is soluble with almost everything except silver, so that's going to be a solid. KNO3 has both the group 1A and the, oh, oops, it's not there, the nitrate. There it is. And so that's going to be aqueous. That's not going to dissolve, or that is going to dissolve. It's not going to form a solid. So my white solid precipitate must be silver chloride. So now if I know that I've got silver chloride, that's my solid product, I can do stoichiometry. So if I've got 50 mils of 1 molar silver nitrate mixed with 25 mils of 1.5 molar KCl, what mass of solid product would I expect? So again, if you were to see a problem like this, I may not even give you the formulas. I might just say silver nitrate, potassium chloride. The very first thing you always want to do for any stoichiometry reaction is, of course, write the reaction down. And so in the previous question, I already gave you a head start on this, right? But it's silver nitrate, aqueous, plus KCl aqueous. We're writing the formula equation again, the full formula equation instead of the ionic equation. And that makes silver chloride solid, we said, and potassium nitrate, which is going to be soluble. It's going to be aqueous. So I need to figure out how much of this I get from reacting these two guys over here. So just like any stoichiometry problem, I want to start by taking my volume of silver nitrate and my volume of KCl and figuring out how many moles I get. Now I don't have quite enough space to do this in a nice way, but I'll try and do it in steps nonetheless before I run out of space. And once I know the moles of each of those, in this reaction it's quite simple because I have a 1-to-1 ratio between each of these and my product. And so whatever moles I have of silver nitrate or potassium chloride, that tells me how many moles of my product I can make. So I just need to look for the limiting reactant, the one that limits how much stuff I can make. So to get moles of silver nitrate, I've got my 50 mils. I got to convert that to liters. To save space, I'm not going to put all the sig figs in there. So 0.05 liters times 1 mole per liter, I get 0.05 moles of that. If I do it with my KCl, I've got 25 mils, so 0.025 liters times 1.5 moles per liter, 1.5 moles per liter. So out of that, I only get 0.0375 moles. So which one is my limiting reactant, my KCl or my silver nitrate? Well, I'm going to run out of KCl first, potassium chloride. So clearly in this reaction, the potassium chloride is going to be my limiting reactant. Once that's all used up, I can't make any more of my product, so I can't even use up all of this silver nitrate over here. So this is my limiting reactant. And so now I can go from that and figure out how many moles of product I'm going to get. So let me erase this, what I've written already, and we'll go back and figure out how many moles of silver chloride I get from this. Oh, and sorry, we already figured that out as well, right? Because we said it's a 1-to-1. So we're actually going to get exactly 0.0375 moles of silver chloride, and then we want to figure out its mass. Okay, so just setting up what we said verbally there, that if we have 0.0375 moles KCl, we get 0.0375 moles AgCl, silver chloride, and we want to convert this to mass of silver chloride. And let's just do this in grams. So mass silver chloride in grams. Okay, so if we go ahead and take the molar mass of silver chloride, we should be able to solve for the total mass that we make. So the mass of silver chloride is 143.3212 grams per mole. So we need to take our 375 moles times the molecular weight or molar mass, which is 143.3212 grams per mole. It's just the mass of silver plus the mass of chlorine. And that comes out to 5.3745 grams, if my handwriting were better, for 5 grams of silver chloride. And we've got only 2 sig figs from the 1.5 and the 1.0, so 5.4 grams of silver chloride. So make sure you can do any kind of stoichiometry with precipitation reactions in that way. So that's all of the basics. If you want to hang out for a couple more minutes and watch some more examples, I'll work through those. And otherwise, you've got the fundamentals down, and we'll move on Friday to talk about redox reactions. But let's do a couple more examples with precipitation reactions if you're interested. So in this one, we're going to try and figure out what the precipitate is in the reaction of potassium hydroxide with iron 3 nitrate. I've given you the solubility rules down here at the bottom, because you'll have those on the equation sheet. So take a moment, pause your video, see if you can answer this question. So this is going to make, by swapping the ions, potassium nitrate and then iron 3 hydroxide. Potassium nitrate, KNO3. If we look at the solubility guidelines, nitrate is soluble, potassium is soluble, so that's going to be aqueous, so that's not our precipitate. Potassium hydroxide was one of our reactants, that's clearly aqueous and not even a product. Potassium nitrate is aqueous. Iron 3 nitrate was one of our reactants, so it has to either be C, iron 3 hydroxide, or E, none of these. And so iron 3 hydroxide is going to be FeOH3. Is that solid? Well, if we look at our solubility guidelines, I don't see iron or hydroxide anywhere in there except for these 3 compounds that have hydroxide. So indeed, that's going to be a solid. So the answer is going to be C, iron 3 hydroxide. Let's do another one. So now let's think a little bit again about formula versus net ionic equations. So this question asks, which of the following is the balanced net ionic equation for the reaction of lead nitrate with sodium iodide? Both of those are aqueous. They dissolve in solution. So write down what the net ionic equation is. You have to remember what that means, what the definition is for a net ionic equation before you can solve this problem. So pause the video, see if you can figure that out on your own, and then I'll walk you through it. Okay, So lead nitrate and sodium iodide, those are our reactants. So this first one would be our formula equation, right? Because we've got the full formulas of those two things making lead iodide and sodium nitrate. And that does make sense. So the nitrate ends up with the sodium, the iodine ends up with the lead. Lead iodide is, in fact, a solid because it's on the exception rule here. So iodine with lead, that is a solid. But that's the formula equation. So that doesn't answer this question. Everything starts out aqueous. So we have lead aqueous, nitrate aqueous, sodium aqueous, and iodine aqueous. So this is the complete ionic equation here. So that's also not the answer to this question because the nitrates and the sodiums are going to stay in solution. They're going to stay the same on both sides. Oh, I messed up. That's not the complete ionic equation because it shows the lead iodide as still in solution, and that's not even right. It comes out of solution, so that's just wrong. Let's see. This guy has the lead iodide in the solid form, so there's our complete ionic equation. But this is asking for the net ionic, so that's still not the answer. This one's just wrong altogether, B. And then D has, we should have the nitrates and the sodiums out of there. So we only have the lead mixing with the iodine. That's our net equation. Those are the things that are really changing in this reaction. So the answer is D. So another question for you. Write the balanced net ionic equation for the aqueous reaction of calcium chloride with lead acetate. So take a second, see if you can write that down. And now that you have it written down, tell me what are the spectator ions? So I'm going to give you a moment to answer both of those questions and then I'll walk you through it. And again, you're going to want to pause this if you haven't answered it already. Okay, so calcium chloride, CaCl2. According to our solubility rules, which I don't have on here, but if you look back at them, that's going to be aqueous because it has chlorine and it's not an exception. Lead acetate, PbCH3CO2. And I just realized I made a slight mistake when I wrote this. This should say lead 2 acetate. There's a lead 4 as well, so I apologize for that. I just realized it. So lead 2 acetate, we're going to have 2 of these acetate ions in there. Acetate ions always make soluble compounds because they're just so big, so we've got that. As our formula equation. Now, I'm kind of out of space to write my net ionic equation, but let's give it a try. So if those are my two compounds that I start with, if I write them as ions, we've got calcium 2+. I'm going to just go ahead and leave the state symbols off to make sure that this fits. 2Cl-, a lead 2+. Again, I'd have to tell you that that's lead 2 acetate, so I apologize for that omission. And then we've got 2 of our acetate ions, CH3CO2-, and those are all aqueous. I just didn't have room to put it in there. And then that's going to make lead chloride, PbCl2. And if we look on the solubility chart, that's a solid. And then we're going to be left with the calcium 2+ ions and the acetate ions. Again, I've left off the state symbols because I'm out of space, but those are still going to be aqueous, and we've got 2 of those. So we can say that the calcium 2+ and the acetate are spectator ions, and so that's what the question is asking for. It's calcium 2+ and acetate are the spectator ions. They don't participate really in the reaction. One thing I didn't point out, and I didn't have an example on here yet, was we can have cases where no reaction occurs. So let's look at an example like that. So for the sake of example, let's say we've got the reaction of lithium nitrate. Sorry, I got hung up there a second trying to write that. Plus lead acetate. And I've put the solubility rules back up, and we'll see that both of those are soluble compounds. And if they were to react, then we'd have lithium acetate. Oh, and I forgot to make this lead-2 acetate. We'd have lithium acetate, and we'd have lead nitrate. And I would have to have some other numbers in here to get this to balance out. I would need a 2 there, a 2 over here, oops, not a 2 there, 2, nope, that does it. I've got 2 lithiums and on both sides, 2 nitrates on both sides, 2 acetates on both sides. If I looked at the solubility chart, though, for this, I'd say that lithium acetate, having both lithium and acetate in it, that's going to be soluble. And lead nitrate is also soluble. So there's no reason for these ions to even rearrange at all because they're all just floating around in solution. So if we were to write the net ionic equation, we'd have lithium plus nitrate. We'd have lead 2 plus. We'd have acetate on the left. We'd have on the right lithium 2 lithium plus 2 acetate, 2 minus, plus lead 2 plus 2 nitrate. So there's our complete ionic equation. I don't know if I said net ionic a minute ago, but I meant to say complete ionic. And if I cancel out all the spectator ions, then we see that for everything being aqueous on both the reactant and product side, there is no net reaction. Okay? So if I were to ask you what would be the reaction between these, you would say there is no reaction. There's no reason for a reaction to occur here. Everything just stays in solution. Nothing reacts and comes out of solution. Okay? So we sometimes see that in nature as well. We might put a couple of different ionic compounds in solution and nothing happens. So if neither of them is solid, then they're all just going to stay floating around in solution. Okay, let's look at one last type of example, if you're still with me here, and that is to see how could we make a compound, knowing what we do about solubility of compounds, we could make up a reaction to make some sort of a solid. And this is probably one of the most common applications of precipitation reactions, because someone says, well, I want calcium phosphate. How am I going to make it? What can I combine in solution to make calcium phosphate? So the way we're going to do this is to work backward. We're going to start by writing the net ionic equation to get what we want. So very easy. It's 3 calcium 2 plus aqueous plus 2 phosphate 3 minus aqueous going to Ca3 PO4 2 solid. There's our net ionic equation. Okay? That tells what we want to happen. Then we got to find soluble ionic compounds that give us those ions. We need to find a soluble compound that gives us calcium. Okay? And we need to find a soluble compound that gives us phosphate. And then we want to make sure that the other ions in there are not going to make a solid as well, because we only want one solid. We only want calcium phosphate to get this out. So let's see if we can figure this out. So we've got calcium. What can we put with calcium that it's going to make a soluble compound? Well, maybe a chloride or a bromide, right? So calcium chloride, that's going to be soluble. So we can put calcium chloride in solution to get our calcium ions. And then we need something that has phosphate in it. So what can we put with phosphate that's going to be soluble? I would say ammonium would be a pretty good bet, because ammonium is going to be soluble with whatever. And so if we have NH4, we're going to have 3 of those to balance out the PO4. That's going to be aqueous. I'm going to move this to another screen so that we can see it a little bit easier. Okay, so now we have a little bit more room to work, and we said we're going to try to add calcium chloride aqueous to ammonium phosphate aqueous. Let's see what we get. We get calcium phosphate. Okay, that's what we wanted if we combined our calcium ions with our phosphate ions. And what's the other product that we get? We get, and that's going to be our solid, right? And then we're going to get our other product, ammonium. There's our ammonium with chlorine, ammonium chloride. And ammonium chloride, the chlorine ion and the ammonium ion together, they make something that's soluble, so this works great. Okay, so then let's just balance it out. We've got 3 calciums over here, so we better get 3 over there. We need to have 6 of our, oh, I've made a mistake here. Hold on a second. I got to erase. I don't want 3 phosphates there. I want 2. I need to get 6 of my chlorines now. And so I'm going to have to put a 6 out here to make that work. And then to get 6 NH4s out of this, I got to have a 2 there, and that's going to balance out my phosphates. So now I've got it balanced. So when we're balancing precipitation reactions with ionic compounds, it's usually pretty easy to just balance them. Instead of saying each element, calcium, chlorine, phosphorus, we want to balance them by the ions. We'd say, okay, how many calcium ions, how many chlorine ions, how many phosphate ions on each side, and how many ammonium ions on each side. And that's a lot easier way to balance it if we've got a precipitation reaction. If you have any questions about any of these, let me know before the final exam. Bring your questions on Friday if you want, but I know a lot of people will probably be kind of burned out after the exam. Again, this material will be covered on the final. Good luck on your exam.